Welcome to this lecture series in real analysis. In this lecture, we'll see another criterion for continuity, and let us recall what we need. So we will need the notion of a neighborhood. Given a point x in the set of real numbers, a neighborhood of x is just any open set U containing x. So an open set containing a point is called a neighborhood of that point. An example is the delta neighborhood, which is this thing. You choose a positive number delta. The delta neighborhood of x is this open interval. Okay, we will need the epsilon delta criterion for continuity at a point. So fix a function f and a point x naught in the domain of domain of f. S is the domain of f. So we saw that f is continuous at x naught, for which we had a definition which we called the geometric definition, but it was straightforwardly equivalent to the following statement, that for all epsilon greater than 0, there is some delta greater than 0 such that whenever we choose x in the delta neighborhood of the point, and of course in the domain of the function, we find that fx is in the epsilon neighborhood of fx naught. Okay? And we will need the global definition of continuity, which means what? So we say that a function f from a set of reals to reals is continuous if it is continuous at every point. So first we defined continuity pointwise, and then we just defined the continuity of a function by declaring it to be so if it is continuous at every point in the domain. Okay. So let's get started. Here is our first lemma, and this is interesting. The reformulation from the geometric definition to the epsilon delta criterion was underwhelming, but this is a little bit more interesting and useful also. So fix a function from a set S of reals to reals, and fix a point x naught in the domain of the function. Then the following two statements are equivalent. First is that f is continuous at x naught, which for us means that the epsilon delta criterion is satisfied for this point. And the second statement is that for each neighborhood v of this point, fx naught, there is a neighborhood u of x naught such that this happens. So let me read out the philosophy of it. This is the notion of nearness to the point fx naught, and this is the notion of sufficiently near. So every point in U is sufficiently near to x naught, such that whenever you feed a point from the set of sufficiently near points, you land inside what you fixed as a notion of nearness. So this is exactly following the philosophy of continuity that we discussed, except now we kind of are doing away with exact numbers. So in the epsilon delta criterion, you see numbers, epsilon and delta and so on. But here you're kind of bypassing that. So this deduction is very, very simple. In fact, it is a straightforward exercise, but there is a difference in expression. So let's prove it. So from 1 to 2. So to do this, let V be a neighborhood, or fix a neighborhood V of fx naught. We want to produce a U. Okay, so by the definition of a neighborhood, we can find a positive epsilon such that this open interval is contained in V. Okay, maybe drawing some pictures will be informative. So our function f is from some subset of reals to reals, but for understanding purposes, just think of the domain as the entire set of real numbers, and it is mapping into reals. And here we have somewhere a neighborhood of the point fx naught. Some neighborhood of fx naught has been chosen. capital V. And now we can find a positive epsilon such that the epsilon neighborhood of the point fx0 is contained in V. Fine, so maybe I'll also draw that. Okay. And now what we want to do is we want to produce a neighborhood around the point x0 such that the points in the neighborhood, which are also in the domain of f, map inside the neighborhood V. So that is what we want to do. But now by the definition of, or rather by the epsilon delta criterion and the fact that f is continuous at x0, f is continuous at x0 because we are assuming one. So we know that there is a delta. There is a delta such that whenever we choose x in the delta neighborhood of x0 and x in the domain, of course, we get this, right? So pictorially, whenever we choose anything in the delta neighborhood of x0 and a point in the domain, it goes inside this pink thing. Okay, but this thing over here can be rewritten as that. But at the same time, note that this is contained in V. This in the picture, this is what that is, and that is contained in V. So we can also write this. Okay. So now if we call this capital U, then capital U is a neighborhood of x0, satisfying the requirement of the proposition. So call this capital U. Then the statement is same as saying that this is contained in V. So this statement and that statement are the same. So that proves 2. This is the statement of 2. And for the reverse, reverse is more or less just a small, it's also a small exercise like the previous one, but let me do it just for completion. Okay, so for the reverse, fix an epsilon greater than 0. And just to be very clear, what do we want to do? We want to show that there exists a delta greater than 0 such that whenever x is in the delta neighborhood of x0 and x is in the domain of the function, we have this. So, this time I'm writing it this way. In the previous slide, I had written x in this open interval. It's the same thing. It kind of looks better, I think. So this is what we want to do. Okay, so define capital V as this open interval. So this is a neighborhood of the point x, fx0, and by 2 there is a neighborhood u of x0 such that this is the case. But since u is a neighborhood, we can find a positive delta. Since u is a neighborhood of x0, we can find a positive delta such that this is contained in the set U, and therefore from star we have the thing that we wanted to prove. So this is exactly the same as the orange thing, and that's it. So 1 and 2 are equivalent, and that is a nice reformulation of the notion of continuity. All right. But now this is much more interesting than the previous one. So fix a function from a set S to the reals, where S is a subset of reals. Then the following are equivalent. Let's just focus on the first two first. The first is that f is continuous, which is that f is continuous at every point of the domain, which is to say that the epsilon delta criterion is satisfied for every point in the domain. And the second statement is, let's be very, very careful about this. For every open set V in the set, for every open set V, there is some open set U of R, of course, such that the pre-image of the open set is equal to this intersection. It's not contained or anything, it is equal to it. So here when we said f is continuous, it was kind of a pointwise thing. The epsilon delta criterion is satisfied for every point. But here that pointwise nature seems to have been lost, or we are kind of bypassing it, and that's very convenient. We don't need to say things pointwise anymore. It seems that way. The definition is a pointwise one, but this expression is not a pointwise one, and that is why this is so powerful. So pre-image of an open set is an open set intersection the domain. That's what global continuity is. And the third one is just to replace the word open by closed. And this is just a semantic thing. And so we will discuss the relationship between 1 and 2. So let me go from 1 to 2. And that's what I want to explain visually. And then I will show a formal proof. And whatever I don't show is an exercise, because this is not a hard thing at all. So let me try to explain why 1 implies 2. So we are assuming f is continuous at every point of the domain. Okay, and we want to prove the second one. So fix some open set V. Yeah, so what are these two rectangles trying to depict? So to explain the proof, I will use this picture. So this rectangle denotes the set of real numbers, which is a very unusual way of thinking about real numbers, but this will help us appreciate what is going on. So this rectangle denotes the set of all real numbers, and we have some open set capital V chosen arbitrarily. And here is the domain of the function. S is the domain of the function. And the function takes the set S to reals. Okay, and let me draw the pre-image of the set V. So let's say this is the pre-image of V. Okay. So if you take the pre-image of that thing, it becomes this. And now we want to show, we want to prove that this thing is the intersection of an open set of R with the domain. That's what we want to do. So what is the idea? Maybe I'll draw it a little bit bigger. Okay. And what is the idea? You choose any point here, call it X. And now since f is continuous, it is in particular continuous at X. Okay. And therefore, by the previous slide, we can find a neighborhood of X naught, call it neighborhood of X, call it Ux, such that all the points in Ux intersection S map inside the set V. Okay, so there is some neighborhood Ux of X such that all the points in the intersection of Ux and S map inside V. And therefore Ux intersection S must be contained in the pre-image of V, because all the points here are mapping inside V. So this shaded thing has to be contained in the pre-image of V. So the picture looks like this. What we have justified is that there is some open set Ux such that Ux intersection S is contained in the pre-image of V. And that can be done for every X. So if we do that for every X, we will pick up some open set such that its intersection with the pre-image is contained in, its intersection its intersection with S is contained in the pre-image of V, right? So that's what we can do. So for every X, we will pick up such an open set. So for X, we get Ux, for X prime, we get Ux prime, and so on. So all we just need to do is now define capital U as the union of all the Ux's, right? So these Ux's together cover the entire pre-image. And if you intersect this thing with the pre-image, you get the pre-image. That should be clear from this picture. So that's it. That is the proof. I mean, that's the main idea of the proof. You construct this set U as I just explained. And then this is just semantics. Open, closed, complement of open is closed is basically this part. And therefore, these two things are equivalent just semantically. And from 2 to 1, you can easily do. And let me show you the formal proof now. So these are the formal, this is the formal proof for 1 implies 2. This is the formal proof for 2 implies 3. 3 implies 2 and 2 implies 1 are left as exercises. Okay. All right. And now let's look at some examples which we have seen. But let us try to see why this function, the step function, is not a continuous function. And the reason is very simple. If I take the pre-image of this open set, which is half to 3 by 2, the pre-image of this open set is, it is going to be this thing, right? I hope I'm not making a mistake. Yeah, so the pre-image is from here to there, which is not an open set. It is a semi-open set. So pre-image of this particular open set is not an open set, and hence this function is not globally continuous. We haven't proven that it is not continuous at this particular point by this reasoning, but it is clear that this is not globally continuous because you can easily locate open sets whose pre-images are not open. And the same goes for this guy. If you take the pre-image of, let's say, maybe this interval minus half to half, what's the pre-image of this thing under this function? It's precisely the irrationals. So what is this function? Let us recall. This function is, it takes 1 if x is rational and 0 otherwise. And therefore, this function is not continuous because if you take the pre-image of this thing, you get precisely all the irrationals, but that is not an open set. So this is also not a continuous function. So this is so convenient. To prove something is discontinuous, this is very, very useful. You don't need to do some point-wise analysis. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.